Hello, everyone. I'm Mike Pittenger. I'm here on behalf of Insignary, and I'm here to speak about, take on a little bit more about what Taekwon spoke of earlier, which is what comes after the SBOM. See if I can do this correctly. So about me, I've about 25 years in application security, about 10 years in software composition analysis. I was a VP of security strategy at Black Duck and have been an independent consultant to Insignary for about 6 years now. I live in Maine, which is in the northeast corner of the U.S. It's famous for lobsters and lighthouses. And so if you see a lighthouse in this presentation, it's from my town. So that's one. This is a group that has been working on this problem for a long time. These are the early adopters of open source and open source policies. And we've been fighting for a long time for SBOM adoption. And this is not a new problem. This is a screenshot from an article from over 20 years ago where the U.S. Department of Defense and Microsoft and security executives were talking about the risk to security from vulnerable open source components. And this continues to be a problem because while criminals are evil and criminals, they're also rational actors. So they have a choice when they're going to make an attack about whether they're going to search for a zero-day vulnerability in custom code or simply leverage one of the thousands of vulnerabilities in open source, in popular open source components. And it becomes a pretty easy choice from that standpoint. This graph shows that for any single vulnerability that is publicly disclosed, there will be an exploitation, an attack using that within 100 days. So the bad guys know that these open source vulnerabilities are widespread and easy to attack, and therefore they do that. So this is being driven now by a lot of concern around supply chain security within both government agencies and corporations. But we are beginning to make progress. In the U.S., as Taekwon mentioned, we have 3 initiatives undergoing. So after the Colonial Pipeline attacks and the SolarWinds attacks in the early part of this decade, President Biden issued Executive Order 14028 for securing the nation's cybersecurity. And one of the requirements of this will be to provide SBOMs for all software or products containing software provided to U.S. government agencies. And that's in the rulemaking process right now with the Department of Defense and NASA, and also with the General Services Administration, who is responsible for much of the software acquisition within the U.S. government. The Secure Software Development Framework, or SSDF, is another initiative, and it is, its goal is to make sure that software producers are properly incentivized to build secure software. And this includes penalties on them for not building secure software. The requirement will be to follow NIST 800-218, which is the Secure Software Development Framework, and it also includes the requirement for an SBOM. And finally, the Food and Drug Administration is requiring SBOMs now for all pre-market submissions for if you want to do a new infusion pump or a patient monitoring system or any type of software device or software device that includes software for the medical field. Europe is a bit more streamlined. As Taekwon mentioned, they have the Cyber Resilience Act. This is a requirement for virtually any software. You can see the display on the right. So it covers everything from mobile applications to operating systems to industrial control systems. Annex 1 of that act outlines the essential cybersecurity requirements that organizations must comply with as part of the CRA. And that also includes providing a software bill of materials. Non-compliance with this is similar to non-compliance with GDPR. So it can be fines of up to 15 million euros, or the greater of 15 million euros, or 2.5% of the organization's worldwide revenue or turnover. So pretty strict. In Asia, as you probably know, we have a couple of recommendations or guidelines coming on. In Korea, we have the software supply chain security guidelines, and in Japan, we have a guide to implementing software bills of material. The guidelines from Japan are broken into 3 phases, where the first phase is familiarizing yourself with the tools that allow you to build an SBOM and publish an SBOM. Phase 2 is practicing doing that, and phase 3 is implementing that in a commercial setting. So from that standpoint, as a group, we've won. We've been advocating for years and years that organizations need to use open source responsibly. They need to publish SBOMs, and no more hiding behind security by obscurity. So congratulations, everybody. We can now expect a lot of SBOMs. We now will not be restricted to the SBOMs that we produce internally. We will soon have the ability or the requirement to receive SBOMs from everybody we do business with. So this is going to be a major change for us. Today, most organizations are only managing SBOMs that they produce internally. And that's a pretty simple task. You make it part of your software development lifecycle. You use an SCA tool to produce those. You have access to the source code. You have control over the policies on what type of licenses you will allow and what types of security vulnerabilities you can tolerate. But when we go to a world where everybody is providing an SBOM, it's completely different. You may be receiving hundreds or thousands of SBOMs, or have the ability to receive those. This is just a list of the leading IoT security companies from last year. When you start to include commercial vendors and so on, it really changes the picture. You don't have access to the source code. You'll have third-party code that you may be building into your own products. Your vendors may have third-party code that they're building into their own products, so fourth-party or fifth-party code. And you have no visibility to the policies that those second, third, and fourth parties are enforcing or not enforcing with their software. You don't know how they're tracking vulnerabilities. So they may be going to the open source community web pages, they may be going to GitHub, they may be using NVD, but you have no visibility to that. So the fact that we will have access to a number of SBOMs, a large number of SBOMs, doesn't necessarily mean that we're improving our security. So what can we do? If we accept that we're going to be managing thousands of SBOMs in the future, what are some of the best practices that we can begin to think about and begin to implement? So I'll outline these briefly and then go into more detail. First is to maintain an SBOM for your entire attack surface. Second, verify critical third-party SBOMs. Third, make sure that the SBOM data that you have is actionable. And fourth, have a central repository for maintaining and managing SBOMs. So for the first one, again, we think of SBOMs typically, at least in the organizations I've been familiar with, as SBOMs that are developed internally for software that we're developing internally. That may or may not be part of your attack surface. Your attack surface may include firmware in an IoT device or a router. It could involve commercial software that you license and use to manage critical data. It is certainly your IT environment, all of your infrastructure. And this last part is one that I think is particularly important because the IT environment is largely built on open source. We have Linux distributions and containers and cloud applications and open source databases and Kubernetes and so on. All of this is open source, And importantly, it all bypasses a secure development lifecycle. The IT department doesn't go to security and say, here's how we're going to build our IT stack. They receive an application and they run it. And the way they address security today is, in my view, very backwards. They run vulnerability scanners. So they basically build a rule for each vulnerability that they choose to look for, and then run that continuously across their entire IT environment. And it just seems like a bizarre way to do security. If the automotive industry ran this way, it would be out of business. So think of the analogy. If the automotive industry did this when they had a defective component or an insecure component, say it's an airbag, in order to find out which vehicles it was in, they would have to have every vehicle in the world go to a shop and have their onboard computer queried. That's what a vulnerability scanner does. And they would tell them whether or not that vulnerable airbag exists in that particular vehicle. And the next day, there's a vulnerability disclosed in a starter motor, and the same thing has to be repeated. Every car would have to have their onboard computer scanned to see if they're using a vulnerable version of that starter motor. And the automotive industry solved this 100 years ago by using bills of material. So when there is a vulnerable component, they know precisely which car to look for and contact the owner and issue a recall. If we had an SBOM for the IT environment, we could do the same thing. We wouldn't need to constantly be scanning for vulnerable components. Second thing, verify critical third-party SBOMs. Pardon me. If we're dealing with thousands of SBOMs, it's impractical to think that we could verify all of them. It would be overwhelming. But for applications or devices that are critical to your success, to your organization's security, you should verify those. You need to understand how they're generated and then look for those assets that are most important. These are going to be internet-facing applications, devices that provide ingress to your IT environment, or perhaps binaries that include third, fourth, fifth party code. So as an example of this, I went online a couple of months ago and downloaded the latest firmware releases for 3 very popular internet routers, and I've hidden the names. I ran those binaries through Insignary Clarity, and you can see the results here. Each of these, the latest release of these 3 routers, each contained over 1,000 vulnerabilities, publicly disclosed vulnerabilities. And included in those vulnerabilities were dozens of them where you could go on ExploitDB and download a publicly available exploit to make an attack particularly simple. So this is a big issue. We have focused so far, in most cases, on software. We also need to focus on firmware and devices. Third, the information that we keep on SBOMs needs to be actionable. We need to have information, not just data. So we need to know that the vulnerabilities and the licenses are mapped from reliable sources. We need to know where to look for a new vulnerability as it's disclosed, what products are affected, what servers are affected, is that vulnerable portion of the component being used. And we need to prioritize these things based on these vulnerabilities based on, again, the criticality of these to our organization. So a vulnerability with a score of 7 in an online banking application is probably more important than one with a CVS score of 10 in an internal application. So we need to be able to look at a risk ranking of the components and understand how we're going to go about remediating these. So if you think about it, when you run an SCA analysis and get an SBOM report for a security vulnerability, that vulnerability may be in a component that is 5 or 6 or 7 years old. You don't want to replace a 7-year-old component with a 6-year-old component because you may be introducing more risk than you already have. So look for a solution where you can make an informed decision and where you're getting full information so you can make an informed decision about how you're going to remediate it and which version of the component you're going to move to. You may not be able to jump from a version 1.7 to version 6.5. So you want to be able to look within the version families for the most secure or least vulnerable version of those. And finally, you want to have a single repository for this. So you want to be able to import SBOMs in an accepted format or in a custom format. You want to be able to normalize the data so you know which CPE you're mapping to and which vulnerability and license databases you're mapping to. You need a single point of truth for that. So this requires something more than what we have today in terms of just looking at source code. We need binary analysis to do some of this. So we'll start by understanding how SCA works. Most SCA solutions today work on source, and they work on source as the developer designs it or as built. Two major approaches. You could parse a package manager. So this is the instruction set given to the build system for what open source components that they need to fetch in order to make the software run. And it's a very quick, largely accurate way of doing that. It has a couple of shortcomings in that if a developer elects to compile code directly into the software, it will not show up in the package manager. And it can't be used for languages that don't have a package manager, like C and C++. A second approach is hash matching, where the SCA vendor will generate lists of hashes for components and subcomponents and metadata and so on. And then when they scan the code, they generate those hashes again and match them to their database of hashes. This can be more complete if used in combination with package manager parsing, but it's a difficult problem because there will be a unique hash for every processor compiler combination, so it can be overwhelming to try to have a complete knowledge base of all possible hashes. So binary SCA can build on those solutions and provide deeper inspection. So I'm describing how Insignary Clarity does it today, but the system or the idea is the same. First, if the package manager is available, examine it, parse it. Just begin to build a candidate SBOM from that. Second, run the hash thing and bring more information into the SBOM so you can start to make better decisions about versions and so on. And finally, scan the binary to extract fingerprints of artifacts and strings and items from the source that survive compilation. So there will be unique strings or artifacts that are the same in the source code as they would be after they are compiled. And there are hundreds or thousands of those for each component. And this can help you narrow down the candidates for the SBOM and provide a more complete picture of this, in particular if you don't have any access to the source code. And this is all done without any reverse engineering techniques that would violate an end user license agreement. This provides a lot of benefits. Number one, if you're looking at, if you don't have easy access to the source code for an application within your organization, you can examine the binary and still produce an SBOM. If you have a critical application or device from a vendor that you're using in your infrastructure or embedding in your product, you can build an SBOM for that or verify an SBOM that you've received. You can have fewer false positives because the binary analysis gives you the ability to look at which portions of the vulnerable component are actually used. So you can determine where the vulnerability exists within the library and determine if you're actually using that or not. And if you're not using that portion of the library, ignore it. And like other SCA solutions, it allows you to maintain continuous monitoring of the security without having to rescan. So as new vulnerabilities are disclosed, you can receive alerts for both your applications, your devices, and for your IT infrastructure. So this is right down the road from my house. That lighthouse was commissioned by George Washington in the 1700s. So it's new for Seoul, but old for us. Thank you very much. If you have any questions, I'll be here for the rest of the day. Thank you.